This talk will be a bit complementary with what Claire explained with his two first talks. It's about, the first one is about icing in supercooled large droplets, ice crystal icing condition and snow condition. And we'll see how the classical icing, which has been presented by Claire, cannot be applicated as well for this condition, and how we have to modify the models and the codes to deal with these three kinds of icing conditions. So to begin with, a few definitions of what we call SLD, ice crystals, okay, and snowflakes. Everybody is aware about that after 1 week. Okay, but just to be very quickly, I will go on that very quick. A supercooled large droplet, SLD, the droplet for which the diameter is assumed to be 50 microns. It is what is assumed by the certification rules. And for us, this kind of droplets have a complex interaction with the wall. In classical icing, we assume in the code that the droplet full sticks to the wall, and now with SLD, large droplets, large velocity, there may be complex interactions such as re-emission and partial deposit. And in the range of SLD, there are two subcategories, I would say. The one, the freezing drizzles, where the diameter is larger, quite larger than 50 microns, but less than 500 microns. And the bigger ones, more related to rain and freezing rain with diameter larger than 100 microns. So here we will deal, I would say, all the range of quite large particles larger than 50 microns. What an ice crystal, once again, everybody knows, but what we call ice crystals in the numerical codes we use, these are particles which diameter is around 100 micrometers. They are non-sphericals, which will have a large influence on a lot of models for us. They are present at high altitudes where liquid droplets are no more, and low temperature. And the main point for ice crystals is the characterization of existing liquid water, since, as we will see, it's the main point for ice particle, ice crystal to stick to the wall for erosion and stick like that. So to characterize liquid water is the key point for ice crystals. And for snowflakes, so we had a wonderful presentation on snowflakes. So I will not dare doing anything else, but just sum up. The snowflakes, what we want to focus on, I would say, are aggregates. Why? Because in the atmosphere, for an airplane, it can be shown that it is the most frequent population. More than 60% of the particles are aggregates. Okay, and which very large diameter compared to ice crystals, which are 100 microns. The diameter may be larger than 1 millimeters. And difficulty for us is that the bulk density of the particle is very low compared to even ice crystals, which are more dense. And this will be difficult as well for modeling and numerical simulation. So why? Okay, I would say for aeronautics, progress are done, funding are found when there are some crashes. And that's what happened for two kinds of particles. For instance, for SLD, an accident in 1994 with an A.Huerre 72 at Roslyn in the US. And what happened due to SLD large droplets? They observed a loss of control attributed to a sudden and unexpected hinge moment reversal. And what's the main thing, that they observed a ridge of ice which accreted beyond the de-ice boost. Here you can see the de-ice boot, and they saw some kind of a ridge of ice behind of it. And this kind of ice shape is terrible for the lift coefficient, and the plane just fall down. And first thing, and then what they observed, that the size and the water content, the amount of liquid water in the clouds, really exceeded those described in the icing certification envelope. That's why both FAA, which is the American federal organization for aviation, and both EASA, the same thing in Europe, decided to modify certification rules and to run a project dedicated to SLD. Okay. So, as a conclusion, there are now unusual droplet diameter and liquid water content that had never been expected to happen. The problem is that the ice protection system, which have been developed for classical icing, are poorly qualified for the regime of SLD, and that just justifies the SLD. Yes? Maybe it happened. Sure, it happened before, but it's the first time there was an accident. There was an observation, so, and they asked why it happened, and they discovered it was due to SLD. Yeah, I think so. To be honest, I don't really know the historical aspect, but I think it is the first time such an accident due to SLD, and they understood that it was due to large droplets. Same thing for ice crystals. It is not good news, but due to the Rio-Paris flight, Air France 447. And the conclusion from the BAA report, the agency who lead the investigation, that there was an inconsistency between the measured velocities, probably due to the clogging of the pitot probes by ice crystals. That was the first thing. Then, second thing, that the exact composition of cloud mass in the atmosphere is poorly known, especially with respect to the level of supercooled water ice crystal sharing in a particle their size. So two things. That first, they discovered that even when the ice protection system was on, they may have severe accretion. Because as we can see, the dry ice crystals stick to the heated walls and clog the probes. First thing. And second thing, which we developed another part of the studies, it was to be able to, with satellites and with radar, to localize the cloud where there may be some ice crystals. So, as a conclusion, there is a particular behavior of ice crystal with respect to liquid droplets. The liquid water is the main point, as I said before. What is complicated is that the combined presence of both liquid water and solid ice may lead to an additional complexity regarding ice crystal accretion. And as a conclusion, ice crystal icing is mainly a problem for both probes and both for engines. For wings, because it's bouncing on the wings and they cannot clog the probe, they cannot clog the engines. And finally, for the helicopters, the problem is more due to snow problems. One observation made in 1986 in the US by an Admiral James Gracie, who say when they made some tests with this Dolphin helicopter, he observed that the snow problem was the snow accumulates in the inlet and then breaks off. The inlet of the helicopter who just breaks off, and the engine had to stop. So that's why we had to focus on snowy condition. And as you can see, the main problems in near the ground, when the water blow up a lot of particles, a lot of snowflakes, and in this kind of configuration, snowflakes may go into the engine. Okay. So now the specificities for SLD, ice crystal, and snow in the accretion process. They appear in all the steps from, I would say, injection of the particles up to accretion here. First, during the transport steps, where there are a modification of the drag law for the particle, heat transfer and phase changes, of course. And then at impact and even at the accretion model, where there may be some re-emitted particles, we can go downward, led by the airflow. There is a partial sticking efficiency of the particles, which may be difficult, as Claire showed, that it is a main input of the accretion model, so we have to characterize accurately this one. And due to solid particles, there are some of erosion process which may happen with these typical conical eye shapes, which have to be characterized. Alors, on the transport models, as you know, for aggregates, there is a wide variety of shape for snowflakes, and particularly for aggregates. And what we have to have in mind is that the code we propose when I were at A.Huerre are for industrial application, and it's not the way, it's not possible for them to describe accurately each snowflakes, to have the precise drag of each snowflakes. They ask us some kind of macroscopic models which take into account the variety of snowflakes with minimum degrees of freedom to characterize the particle size distribution. So when we have such kinds of variety of snowflakes, it's quite a challenge to do that, but we have to do to do that. And on other things, the density of the particles, which is very difficult to estimate, because when they provide us some pictures of snowflakes, very often we only have 2D pictures. For instance, they say, okay, this is the kind of snowflakes we have, give me an estimation of the bulk density. So we have to recompute 3D shapes and things like that. The bulk, yes, exactly, yes. I will show it. What we decide is to define a spheroid around it. In Germany, the colleagues from TUDA, they define the convex hull. It's quite similar, but you're right, you have to define an envelope. Now, regarding the impact, here is the impact, for instance, for SLD, a droplet. As contrary to small ones, there is a partial deposit on the wall. Secondary droplets are re-emitted in the domain. There is a partial deposit, so in the sticking efficiency, we have to propose model as well. Okay, and for accretion, what has been shown by Claire as well, there are some kind of typical eye shapes here. This is due to erosion, which is not observed with a small droplet, where we have smoother shapes. Another thing which is really typical of ice crystal has been called like that the first time by Tom Curry from NRC Canada. He calls that the plateau effect. That is to say, when the liquid, the amount of liquid in the impacting particle, what we call the alpha here, when it increases, to begin with, the eye shape increases when the amount of liquid water up to a plateau, and when the liquid water increases more again in the impinging particle, the ice shape decreases. So we will explain it later, but there is a kind of plateau which is really typical of ice crystal icing. Okay, now we have the changes which appear in the transport step and then in the accretion step, how it happens in a typical engine, for instance, for ice crystal icing. Suppose you have solid particles, because they are solid in the atmosphere. They hit the fan, the larger wing in the engine, and it fragments behind the engine here. And since due to the compressor, the engine is a hot environment, of course, and since the typical size particle has decreased due to fragmentation, this particle starts to melt in this area here, and then they hit a static part of the engine, and they were partial liquid water, so they start sticking to the wall where there is no ice, and the liquid film appears due to sticking of the ice particles, and since the environment is hot. Due to this particle, which I score, some heat is drawn from the wall, and little by little there is some ice which appear on the wall. And as you understand, because of the hot environment and because of the fragmentation of the fan, we can observe some ice accretion inside the engine, and this ice accretion, two things. First, it may clog the wall, and it happens. And second things, you have a lot of a large amount of ice which accretes in this zone, and after a while there is some ice shading. With large ice blocks, we go downward in the engine, so that's not good at all. When there are some kind of big ice shapes who go downward, I let you imagine what may happen. Alors, here is oh, ça marche. Sorry. Here is a video, an explicative video made by NASA. Of an engine. So here you have a typical engine with ice crystal which impact. Here is the fan, the larger one with fragmentation. So the typical dimension is a smaller one. And here you have ice accretion on the static part of the compressor in the engine. And as you can see, there is ice growth up with shading. We may impact downwind. The flame out of the engine. This is an illustrative video. Okay, so now to go more deeply, I will present the adaptation for trajectories and for impact, and finally for accretion. Regarding trajectory, as I say, it is something which is already presented. This is a diagram, given the altitude and the supersaturation level, of course, there are different shapes of ice crystals. It has been described very well previously. And as I said to you, the industrial partner asked us to minimize the number of geometric descriptors for the parameters. We remained 3 ones. First, the particle equivalent diameter, the particle sphericity, and the particle crosswise sphericity. And from these 3 parameters, we should be able to adapt all the models from classical droplets, I would say. So what is what is the particle equivalent diameter dp? Here is, for instance, a snowflake which has a volume Vp, an external surface AP. The diameter dp is only the diameter of the spherical particle which would have the same volume Vp. So very, very simple. And the sphericity is only the ratio between the external surface of this equivalent sphere divided by the real external surface of the particle. And it is between 0 and 1. And the lesser phi, the farther you are from a spherical droplet. It was not enough dp and phi to describe a particle, and we introduced an orthogonal sphericity, for instance, for drag coefficients, because we need the orthogonal surface to the related fluid velocity. So here is the snowflakes, here is the direction of the airflow, and A orthogonal is just the projection of the shape in this on this plane. And phi orthogonal is just the ratio between the disk, the surface of the disk of the equivalent spherical droplet divided by this surface. So very few geometric descriptors to be able to describe particles. So what we did, we use there exists some drag coefficient CD for the movement of the particles, which depend on of course particle Reynolds number and the 2 geometric descriptors phi and phi orthogonal. And what we try, here is a cylinder, and we made experimentally, we made an impact on the ice particles here, and then after we measure its trajectory. Sorry, it's a bad quality for the plot. For the experiments, here it is in black here, and the particle hit the wall, and it goes downwind. The Schiller-Hennemann, that is to say the typical drag law for a spherical droplet, is in red, so it's bad. Okay, so we can't expect using classical drag laws, and when we use this kind of drag coefficient, we see that we are not so far from the reality. This is for ice crystal, and we see that we can use quite large spherical values, larger than 0.07, which is not so far from a spherical description, which was quite encouraging for us. But when we try that here on the right for light aggregates, So there's very complex shapes with a bulk density very low. We had to decrease this sphericity from 0.07 around up to 0.2. This is a very disturbed one to be able to capture the terminal velocity of the snowflakes with the models. Here is the numerical terminal velocity versus the experimental one. And we say that the error bar, I would say, is around 30%. That may be quite large, but believe me, that's not that bad for this kind of particles. So, already difficult for ice crystals, quasi impossible for snowflakes. That's why we tried another approach for snowflakes for the drag coefficient, an adaptation for light snowflakes we use to perform an equivalent particle from the single picture we obtained from the flight test. Here is a typical image we have. So we perform the two diameters F max and F orthogonal max, and we perform two spheroids from this one. The one whose the rotation is around the main axis, it is this one, the prolat, and the one where the rotation is around the minus axis, which is the oblate spheroids. And okay, for the results on terminal velocity, I would say the results are quite similar than when using this kind of law, but now we do not need to decrease so much the sphericity, which were not very realistic. And now the idea is that we try to model every snowflake by an equivalent spheroid or an equivalent particle with a convex hull, and we are in the margin of 30%, which is the range which is acceptable by the industrial partners. As you see, the amount of liquid water available is of primary importance for sticking of the particles. That's why we had to adapt the model to predict the liquid water which appeared when the ice particle melts. So the idea is we have a fully glaciated particles, and the model we propose that after a while in a hot environment, it is composed of an ice core surrounded by a liquid film up to a fully spherical droplet. And what we propose that at the beginning we have the sphericity of the particles, which is lower than 1, up to the ends, which is equal to 1, and we have the sphericity which increases up to 1. And here is the law for heat and mass transfer for the particle, very simply, and where the changes have to made at two positions. First, we had to modify the exchange surface of the particle, since it has been enlarged due to the complex shape. And this is taken into account by phi. This parameter is a geometrical modification to take into account the complex shape. First thing, second things, in the Nusselt number, we had to modify the cross-link correlation, which is typically used for spherical particles. And by an analogy, we propose this model to take into account the complex sphericity. So a geometric one, and I would say a more thermal one. Sorry, excuse me. Warm environment, that's a good question. I think I will answer it just after. It is an environment where the wet bulb temperature, that is to say, it is the temperature which is the balance between evaporative cooling and heating from outside, is positive. I will explain that, but this is the temperature which is used by engine manufacturer to be more precise of whether or not the particle will melt. To test the model, we used an acoustic levitator that has been done by Airbus Group Innovation in Germany. So you have an acoustic levitator which allows a particle to levitate. They place it in a heated environment, okay, and they control humidity from 4% to 80% to manage this wet bulb temperature and to manage the say the evaporative cooling. And here is the projected area of the particle. So you have a complex shape which melts, and after a while it becomes spherical, and they are able to measure the typical melting time. And what we did, we compare the experimental melting time versus what we call the theoretical, to say the solution of this equation, and we see that that's not that bad. Except maybe for larger times. Why? Because larger times correspond to the drier conditions where the evaporative cooling is very strong, and where the model is it is the limit of the models, and the main discrepancies appear at low relative humidity. For snowflakes, this model did not function at all. That is to say, the estimated melting times were not the good ones. So we had to work on, I would say, the density of the particle during the melting process. In the previous model, just the density of the particles is just very simple law between the density of the initial particle, the density of the liquid water, around 1,000, and the weight due to the liquid fraction of the particle. It is a linear evolution of the density. The results were quite bad, because we measure the evolution of this bulk density, assuming the equivalency with a spheroid, and we see that better we have to correct the density of snow between, I would say, a more sharp increase here near the inflection point between fully glaciated and fully melted part. Here we have to adapt a law. And just a few minutes, sorry. Okay, and that's what we did here. For instance, we compute the numerical time versus the experimental one. And for instance, for the Mitra model, which is the classical one, there was around 60% of error, which is quite large. The core one, what I call the model we propose here, is now 22%. So the errors on melting error will be divided by 2. Just due to an evolution of the bulk density, which is more accurately estimated. Okay, that was for trajectory, and now I would say more difficult, the impact, the changes which have to be taken into account for impact. Alors, the key points for whatever SLD, a droplet, whatever nice crystal, for our application and to feed the accretion model is to estimate the sticking efficiency. Sticking efficiency is just defined as the amount of liquid, the amount of particle which remains stuck to the wall, divided by the one which impacts the wall. Okay? A full deposital epsilon s equal to 1, and if all the droplets are emitted, for instance, for bouncing, epsilon s is equal to 0. This is the first key point. Secondly, we have to characterize as well the secondary, the emitted particles, because as they are emitted downwind, they may impact aeronautical surfaces downwind. And we see that not that easy, for instance, for the Weber which are taken into account. For instance, here you have increasing time, increasing Weber. We see that for a Weber of around 3,000, we see again the classical corona shape after the impact. But when we increase the velocity and the Weber number, we more have prompt splash. So from this kind of impact, we have to characterize first the particle size distribution and as well the velocity distribution after the effect. And this is exactly the same thing for dry particle. It is the impact of nice particles, where you have some fragments which have to be characterized after the impact on the wall. Just to have order of magnitudes in mind, here is the regions which is of interest for the aeronautical applications. This is a diagram with Reynolds and Weber number, and we see that the regime which is interested for aeronautics, I would say, is 10 at the power 5 regarding Weber number, so quite larger. And that's why that has been presented by Claire yesterday. A nice wind tunnel has been developed at A.Huerre to reach this kind of Weber number, because, for instance, here are some examples of databases which are available in the literature. And none of these were able to catch such kind of velocities which are interesting for airplanes. Alors, now we focus on the sticking efficiency, especially for SLD. And what is observed is, for instance, it is the eye shape for a given velocity. For same profile, same temperature, just we increase the diameter of the impinging particle. So we see that there is a large influence on sticking efficiency. Here, for small droplets, we are quite glazed. As if you remember what Claire said, we have a glazed eye shape with a full deposit. And for quite larger diameter, it's not more the case. A lot of ice, a lot of droplets, liquid droplets have been re-emitted downwind. First thing. Second thing, what we see, and that was the problems with the A.Huerre, the impact is beyond the ice protection system, just because to the greater inertia of the droplets and the Stokes number of the droplets, which go beyond of the protected area. And to be honest, to build model for epsilon s, it's not that easy, because experimental estimation of this coefficient is not straightforward, especially for large velocity. How we try to perform model for epsilon s is to combine both numerical and experimental aspects. The deposited mass is estimated experimentally. I will explain that. It's not very accurate sometimes, but okay. And the impingement rate is numerically estimated, and that's quite easy to estimate this flux. This flux is badly estimated, this one quite good. Alors, we tried three different things for estimate the deposit. First, we use a direct measure to try to collect the amount of liquid water which deposed on the wall by collecting tank. Another one, the use of an absorbent blotter paper, which have been stuck on the profile to collect the water. This is an idea of the NASA. That's why. And third one, we use a particular condition, Rime ice conditions, to estimate ice accretion thickness and to derive this sticking efficiency. So the first one, the direct measurement with the collecting tank. So here is an experiment. You have here the wind tunnel. Here you have the flat plate, and here you have a droplet which impacts here and which is able to splash. And here is a small hole, which is here where the remaining liquid water is catch in this tank, and after it is weighed to estimate it. Bon. There are main drawbacks with that. First, there is a strong influence of the airflow, because you have an airflow, some liquid is swept by the airflow, and it just goes away from the experiment, so it's not very good under control. Second things, we have to control the humidity level, because they may have a non-negligible part of the liquid which evaporates. And other thing, it's difficult to discriminate between the deposit for the primary and the deposit from the local secondary impact. This experiment has been calibrated so that the secondary should go outward, but you may have some local. Imagine a small droplet who is emitted normally, it may re-impact. So what is the difference between primary and secondary impact? Not that easy. And of course, it is all the more precise, and the impact occurs at low velocity. Second techniques, the blotter paper. So that has been done in the NASA wind tunnel, where they stick a kind of a blotter paper here. They put some dye in the liquid droplets, and after they took back the blotter paper and they measured the amount of liquid water inside this blotter paper. As you can imagine, there is a very strong influence of the absorbent properties of the blotter paper. For instance, here is a view of this paper. So there is very irregular form, which may be of the thickness of the impinging droplet. So, okay, and it leads to an overestimation of the sticking efficiency. For instance, here are experiments for blotter paper. We see that at large velocity, there is an asymptotic behavior, and 85%, it is estimated that 85% of the liquid water sticks to the wall. We performed the same one with aluminium, and it was not 55, but 60. Okay, so there is a quite difference. This is due to the absorbent properties of the blotter paper. So what is a bit embarrassing, to be honest, that the blotter techniques has been the pioneering techniques to estimate the sticking efficiency during, I would not say decades, but not so far. So when we realized that there was so much influence, all the sticking efficiency had to be recalibrated. And finally, another one to estimate the sticking efficiency is to use the accretion thickness, but in the rime ice regime, where you have no liquid water. Why? Because in the classical mass balance, the accretion rate is just the deposited rate minus the evaporation rate, which is disregarded here, and the run-back rate, which is equal to 0 for rime ice. So the deposited rate is equal very simply to the accretion rate and to this to the ice thickness. Main drawback, we have to know this. The rime ice density. Once again, there exists some correlation to define it. Some people have tried to take the rime ice, the accreted shape, to put it in a bath to estimate the density. Well, this is the weakness, the estimation of this one. And puis, second one, we need for geometries that minimize local re-impact. Bon. And here we have an unsteady behavior, an unsteady evolution of the ice thickness, which allowed us to estimate this deposition rate. Some results. Here is the collection efficiency on a profile. Here you have the chord. At 0, you have the leading edge, the stagnation point on the profile. Here you have the suction side of the profile, the pressure side of the profile. And here is the amount of liquid which is deposited. The red the circles are the experiment. In black, in a solid black line, it is the model where you assume that all the particles stick. So you see that you really overestimate here the amount of liquid droplets. And then when you apply SLD model, which is not that bad. And especially, it is the same thing here for another profile, other conditions. The main improvement of these models, I would say, is not the estimation of the sticking efficiency near the leading edge, near the stagnation point. That's very tricky to obtain this. But what is interesting that the models are quite good to estimate the captation limit, to reduce the overestimation of ice accretion far from the leading edge, very far downstream to the profile. So as a conclusion on that, to say that all the models are models from the zoology of the models of sticking efficiency. These are very correlatory models, and I would say that we never succeeded, and no one never succeeded proposing a very theoretical approach for the sticking efficiency in this kind of regimes. The impingement limit is quite good, accurately taken into account. That is to say, the grazing impact with bouncing is not that bad. And once again, near this point here, it's It depends a lot on the nature of the impacted wall. That is to say, what we observe for the blotter paper, it is the same thing for if you have a clean wall or an accreted one. Sticking efficiency for the ice crystal. The fundamental point is the role of the liquid water in the collection of ice crystal. That is to say, for ice crystals to stick, we need liquid water. And there is 3 possibilities for liquid water to appear. The first one, we may have, I would say, partially melted ice particle that is shown here. We have an ice core with a liquid around. It is the glaciated regime, to say when you have in a hot environment, we have both liquid and solid. Or you may have the mixed phase regime where you have both solid ice and both liquid droplets which are mixed together. This is the first way for the ice particles to get to liquid water, first thing. So this is this one. First, they may have capillary ascent of the liquid water at the wall obtained from ice melting due to head flux at the wall. What when I say, if, for instance, if you have an ice layer and if you have heating, due to ice protection system, you have some liquid water that appear, and as you have a porous ice layer, there is some capillary ascent from of the liquid water from the bottom up to the top, and this made possible for ice particles to stick. And second one, this was a question from Christophe. If you are in a warm environment air with the wet bulb temperature which is positive, what is this wet bulb temperature? Is just an equilibrium between evaporative cooling and heat transfer, which may be written like that. You have evaporative cooling, and you have just heat transfer coefficient between your temperature and the heated temperature outside, and this is the balanced temperature. It's interesting this temperature is interesting, for instance, because you may have a wet bulb temperature which is negative in a warm environment upper than zeros, because you have very low humidity. So, and this is the first information which is used by engine manufacturers to say whether or not they will have ice accretion. If the wet bulb is positive, it's a good indication to know whether or not there will be accretion. A few words about sticking efficiency for ice crystal. There was some experiments performed at NRC, Canada, and they show that the sticking efficiency is an increasing function of the melting ratio, so the amount of liquid water in the particles. Okay, these experiments are very interesting, but they are maybe questionable because here the sticking efficiency is measured from experiments, and how do they make the difference between sticking efficiency of the particle and erosion? That's not that easy. Okay, now to characterize the re-emitted particles, here is a numerical simulation to justify why we have to know the particle size distribution of the emitted particle. Here you have a high lift wing configuration with a flat and slat and main body. The color is the diameter of the particles. What we can see that when you have an impact on the slat, here the particles are re-emitted, smaller one, and here they can re-impact downwind here, maybe the main body and the flap here. So that's why it's important to know the particle size distribution of re-emitted particles for design of ice protection systems. To do that, PDA is used to characterize the secondary droplets just after an impact on the wall. And what has been obtained is represented here. It is the diameters of the emitted particle versus the Weber number, the mean diameter and the Sauter diameter of the particles. And here is 2 databases. The first one, which has been obtained in a project where the velocity were not so high. We thought that there was a kind of a plateau here, an asymptotic, and it was confirmed with a new database where the velocity were quite increased. So there is a decrease of the mean diameter of the emitted particles with a plateau at large velocities. For the emitted particles, as well, there is an influence of the surface which is impacted. For a smooth, clean surface, it is in red. For a nice surface, it is in blue. And we can see that the diameter of the emitted particles is quite influenced by the nature of the substrate. Same thing regarding the pressure which is taken into account. And what perspective works, what we're going to do in the coming years would be to study the ratio of the impact diameter and the typical roughness of the substrate on which droplets impacts. But that's not easy to characterize roughness because it's time evolving function. It depends on everything, the kind of ice you have, the temperature, the delay you use to study the accretion, and at one time you may have very small roughness, which is quite smaller than the diameter, so you can use a kind of average roughness that may be good, and after several seconds, due to accretion, roughness may be quite larger, and then you just have to modify the impact angle. So that's why the roughness height is a very unsteady function. Same thing to characterize the re-emitted fragments, but for ice crystals. I would say things are more well understood because we use the theory from Grady, which has been performed, as you can see, in the 80s, as far as I remember, which is based on an energy horizon model. Why there are more results? Because Grady developed these models for military application and to study when in a bullet, and a bullet impact helms or impact something to check what are the fragments, if the guys who have the helms can survive or not. So there was a lot of things which have been done on this field. And to predict the maximum fragment size, there are two main impact stages. First, there is a crushing of the ice crystal with the wall contact. Here, you have an ice particle which impact the wall, and it deforms here, and there is a small region of plastic deformation here with a crushed eye. And there is an indentation radius here, which is given by a theory. And what we need is to use this radius of indentation to estimate the strain rate inside the ice particle, to estimate after, in a second way here, the fragment size using the energy horizon modeling of Grady for explosive fragmentation. This theory is based on cracks who relieve internal stresses and which allows to define a particle size distribution for the fragments. So first step, we have to estimate indentation radius, and this is the input that since the strain rate is a dimension of the time, we have a radius, we have a velocity. Velocity is taken equal to the normal impact of the particle, and we are able to build a characteristic time scale and then an estimation of the strain rate. So here is the indentation radius after the impact here, and here is the strain rate, which is only obtained by the velocity un divided by a, and we obtain the dot epsilon, which is the strain rate inside the ice particle. Bon. In the theory of Grady, the energy-limited fragmentations assume that the ratio between the size of the maximum emitted diameter between the size of the impinging particle is given by this law, knowing this strain rate here. So how it works, that's not that difficult. It is based on an energy criterion for fragment size, and the way is not to pay attention on the microstructure of the impact. At t equals 0, you have a flow inside the ice particles, and after a while we have this flow which propagates with the fragments whose diameter is proportional to time and c, which is the wave speed inside the particle. And to describe and to find the typical fragment size, it is just a competition between the tensile, the dilatation energy inside the particle, which is given by this expression, and just the energy, the surface creation energy here, which is needed to build surface when fragments appear. Of course, there is kinetic energy, but it may be negligible. And that's why, for a long time, we made this error. We tried to make a balance between this energy, surface one, and the kinetic one, building by the impinging velocity of the ice crystal. But it's not the good one, because this typical energy is quite negligible regarding to the tensile, the tensile one inside the ice crystal. And this allowed us to understand how to derive a model for the fragment size. And when we did the balance between this one and this one, we find here this law to describe the typical diameter of the fragment with regard to time, sigma, where sigma is the tensile stress, which increases with time. Oui? You see, what kind of energy, sorry? Okay. We just we perform, and it is just order of magnitude. We did it by hand, and we see that for the given velocities we had, it was there was really 1 or 2 order of magnitudes between the two energies. The hypothesis made by Gradi's. Okay, the diameter is a function of time like that. It gives the stress tensor is a function as well by the wave velocity, the strain rate definition here. And there is two different regimes. First one, if we plot the volume energy with time, we have the tensile energy, which is an increasing function, and the surface creation energy, which is a decreasing one. And here you have the static approach in green. So they may have two things. First, when the tensile energy increase, it may reach the value for a static approach in green, and you have here the tensile energy, which is equal to the static one, and after some calculation, you see that the law between the strain rate and the diameter as 1 to the power. That is to say, here beta would be equal to 1. If now you focus more on the dynamic approach, which is the approach from Grady, just say that this increasing function of tensile energy is equal for a given time to the decreased energy of the ice particles. And after some computation, you find this law, and the coefficient beta is not 1. It's not 1, but minus 2/3. So, what is the reality between here the coefficient equal to 1 and here the coefficient equal to minus 2/3? The reality is between them. And to check that we are not so far, that the two regimes are equivalent are this when these two times for static and this time for dynamic are equal, which is for a typical case in our application for ice crystals which are of the order of 100 millimeters. So that's why it's not that clear that if it could be 1 or minus or 2/3, because 150 millimeters is a typical thickness of the particle we study. So what we did from experiment, we plot this versus this one, and we measured the value of beta, which should be from the theory between 1 and 2/3. Okay, that's what we did with several databases, and it's not that bad. The fitting between the estimation of the fragment size related to the strain rate. And sorry, I don't remember the value of the exponent we found. Sorry, but believe me, it's really between -1 and -2/3. That's sure. Okay. Now, what I showed it was about the maximum diameter. Now, if we focus on the particle size distribution, what is used is to use the approach from Weiss, which assumes that the size distribution is fractal in nature. That is to say that the number probability density follows a power law like that. The main idea between that is very simple, in fact, is that the rupture propagates from the larger to the smaller scales with an identical rupture criterion. And what's interesting for us is that mostly in the same rupture probability at all scales. There is a kind of scaling which is not dependent on the scale where you're looking at. And that's why Grady proposes a loose analogy with turbulence between what he says for the particle size distribution and turbulence during failure, fracture, and successively finer length scales proceeds through a cascade of crack, which is adequate to the decimation as the initial statistic strain rate are achieved. So, well, the parallel may be not so clear, but that is the one proposed by Grady. And once again, when we tried this fractal description for the particle size distribution regarding the databases we had, that was not so bad to characterize the re-emitted cloud of particles. A very few words on the particle velocity distribution. What we proposed is to, as we have a value, an estimation for the strain rate, which is a scale for time, we said that the velocity of re-emitted fragments of of size r is given by this epsilon dot epsilon dot r is the scale for the velocity of the fragment which is re-emitted. We have two components: a radial one in this one, a normal one to the wall in this one. And here we are able to compute a number of average radial here and normal velocity. So here you have just the velocity for one single parameter here. Here is the volume in which it lives. Here is Rf at the power minus alpha. It is just the probability of the fragment to be re-emitted. And here is a parameter to make the velocity adimensional. Okay? So we did that for the radial one, and we did that for the normal one. And very simply, we computed the radial velocity regarding to L. L is more or less the Weber number. The equivalent, L is the equivalent Weber number, but for solid particles. And the model is in blue, the experiment from TU Darmstadt in red. So there are some things to be improved in this region here, but the trend is not that bad. This is for the radial component. For the normal one, it is the result of this integration here, okay? And that's not good, because for the normal velocities, the average coefficient does not depend on the size of the impacting crystal. There is no size of the impacting crystal. It is constant regarding the size of the re-emitted fragment. So it seems a bit too simpler. Okay, so I think this model is maybe quite good for radial. We have to go deeper, but for normal, it should be it should not be accepted. Okay, now regarding accretion, the plateau effect I mentioned at the beginning, and that already been shown by Claire. Here are the experiment made by Curie on a typical conical eye shape like that, and here is the eye shapes which are very sharp. And here are the eye shapes we have when we increase the amount of liquid water inside the impinging particle. And what shows Tom Curie? He observes a kind of plateau. At the beginning, when we increase the amount of liquid water in the impinging parameters, there is an increase of the severity of icing with a plateau here, with maximum severity here, and after, it decreases as well. Why? Because it is a competition between particles taking efficiency and erosion. In the first stage here, we have low melting ratio, low water inside the particles, so we have an increasing sticking efficiency with melting ratio here, and we have moderate erosion. Because we have few water, the ice is strong enough not to be eroded. On the other part, on the right part of the plateau, we have high melting ratio with a sticking efficiency saturation, and of course, we have an enhanced erosion effect, which is very strong, and washing effect. Because of liquid water, there is washing, and the eye shapes is washed by the airflow and by the impinging airflow. Here is the plateau, which is simulated by the code. The first part of the plateau, the left one, is quite good. The plateau itself, not so bad, but the right part, as you can see in blue, the numerical simulation, not very good. We have poor estimation of the right part of the plateau. Why? We understood. Because here, in the erosion model, only the tangential component of the velocity is considered, because imagine you have here an airflow from top to bottom. In the erosion model, we assume that it is only the tangential part which is used to model these eye shapes. That's why we proposed an evolution of this erosion model based on the Finney and Bitter theory, where once again they keep the tangential part of the velocity and the erosion by cutting, where a part of the substrate is turned off after penetration of the particle, and it's due to tangential velocity, but they add an erosion by plastic deformation, and which is mainly influenced by the normal velocity. So for the efficiency of the erosion, we have the classical tangential here, plus the one due to normal deformation. And what has been observed that here, for instance, for the right part of the plateau, it was very bad with the previous model, and now it's quite well taking into account the normal component of the velocity. And why, as well, if you see in the model here, it depends on the Poisson coefficient, it depends on the yield strength of the ice layer. And what we can see that when eta M, it is to say, increases, it is to say here, when you have a lot of liquid water, the stress decreases because you have a lot of liquid water inside the ice, so this parameter decreases, the Young modulus decreases as well. And that explains why the contribution of this erosion part increases, and we have a better estimation of the right part of the plateau. I think I will stop with, and we'll stop after this one. So it is, I would say, very rare, because this is a real engine where they put some camera to record what happens in it. So it is a heated plate, and we have ice crystal which impact, and you have some here accretion, and periodically you can see that maybe there is some ice shading. Right, exactly, yes. You see it growing like that, and sometimes I hope you will see some very ice shading. Bon. Voilà, boom. Il y a un gros bloc. There is a large block who shed here. Okay, and this is the first time that such a kind of video. That is the first time I saw such kind of video with inside an engine to see what happened. Voilà. Make a short break maybe, and we can start after. Thomas? Ouais? Okay.